What are the main properties of ionic compounds? So let's actually refer here to what they have. Okay, the properties of the ionic compounds. It's going to be, first thing I have to mention that I don't see is that it's between a metal and a non-metal on the periodic table. Or has typically at least an electronegativity difference between the metal and non-metal is typically greater than 1.6 difference in electronegativity, because sometimes we're dealing with trickier things here where it's like silicon bonded with oxygen, and silicon is technically like a metalloid, and that one skates the line of whether it's an ionic bond or not. But because the electronegativity difference 3.44 minus 1.9 from the silicon, 1.54, this would be a very tricky thing to say whether it's an ionic compound or not. But this is kind of how we base it for this. Because silicon is a metalloid, I personally would say that this is still an ionic compound, but I may be wrong, because typically you can tell which ones, like when they have non-metals bond, those are definitely not ionic compounds. Like CO2, carbon dioxide, that is a molecular compound. Nonetheless, in terms of how they bond, as they said here, they form crystal lattices. So it's kind of like instead of it being kind of like a molecule or whatever is bonded type of thing, like when we have carbon, like this would be C4H10, like butane, for example. Okay, this would be like its molecular structure. Usually ionic compounds like NaCl, okay, would kind of form like Cl, and then this would be like Na, and it would kind of keep going like that. It's like it's a weird way to put it, but exactly, it's kind of like that. It's just the crystal lattice structure where you keep switching between Na and Cl, and it keeps going on. It's like a sheet of sodium chloride continuing on and on and on. And that is what they mean by the crystal lattices. They have high boiling and melting points, since ionic bonds are actually the strongest type of intramolecular forces. It goes from non-polar covalent to polar covalent to hydrogen bonds and then ionic bonding. To break an ionic bond, it takes quite a bit of energy, because of the fact that at that point, those two, the metal non-metals that are bonded together, the metal has effectively given that non-metal the electron. It said, here, have it. I'm actually comfortable. I don't want it. And that non-metal is actually happy to receive it. So to then send some energy in to pretty much say, nope, both of you have to keep your electrons of what you originally started with, it takes a lot of energy to do that. So yes, that is why it has the highest temperature required to break it. Ionic compounds have higher enthalpies of fusion and vaporization. Same reason, because ionic bonds are just the hardest to break, and they take the most energy to, I mean, not the most energy, but when they are formed, that is the strongest type of bond there is. It has the most energy in it. Ionic compounds are hard and brittle. Think of it exactly like salt again, forming that crystal lattice. That's the reason why it's brittle, just because that crystal lattice structure allows it. If you really zoom in on salt, you'll see kind of like it goes like it's like striated, and then it's like that, and this would be like a gram of salt. If you look really close, it would kind of look like that. I wish I could show you actual pictures of it, but that's what makes it for its hard and brittleness. Ionic compounds are good conductors of electricity. This ties into the whole how the electrons are distributed, because it's a thing where it's complete donation of electrons to the other one. There are a lot of positive and negative charges on it, which allows electricity to be able to conduct and flow through it. Like the electrons, because the electrons are kind of just everywhere, really. There's a base, and I'm putting on the CL because that's actually where the electrons would be, and there's a way for electrons to be able to travel through this whole crystal lattice structure. And exactly, and this can be actually shown when dissolved in water. We have the Cl ions, and we have and then we have the Na plus ions as well when it's dissolved in water, which allows the electrons to be able to flow through and everything. And more of our ionic compounds are also good insulators. That one, not really sure. Well, I mean, the rest of the list is correct, so I'll have to assume this is correct as well. But the point being, though, the one you have to really focus on is the crystal lattice structure. It is between a metal and a non-metal, okay? And the last thing is that it's the strongest bonds, which is ionic, meaning, as it says there, high melting and boiling points. So that's what we have for ionic compounds. So this is correct. Now move on to question number 19.